The morning of July 2nd, 1943, Yokosuka Naval Air Technical Arsenal, 30 miles south of Tokyo. The summer heat makes the corrugated metal hangar shimmer, but inside, the air is cool, almost reverent. 37 engineers stand in a loose semicircle around an aircraft that shouldn't exist, not here, not intact, not available for study. The Grumman F6F Hellcat sits on wooden blocks, its wings removed, fuselage panels stripped away like skin from bone. Every surface bears measurement marks in white chalk. Cameras on tripods surround it from every angle. The engineers hold notebooks, calipers, micrometers. Some haven't slept in 2 days. Lieutenant Commander Minoru Genda walks slowly around the aircraft's nose. His footsteps echo in the cavernous space. Genda helped plan the attack on Pearl Harbor. He understands naval aviation warfare better than almost anyone in the Imperial Japanese Navy. He's here because this isn't just another captured enemy fighter. This is the machine that's been systematically destroying Japanese air superiority across the Pacific. The aircraft that turned the Americans from underdogs into hunters. What these engineers are about to discover will answer every question the Japanese High Command has been asking for 6 months. They will understand, completely and precisely, why their vaunted Zero fighters are falling from the sky at rates that make no tactical sense. They will see the future of aerial warfare laid bare before them, measured and documented down to the millimeter, and that knowledge will change absolutely nothing. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Because sometimes the cruelest intelligence isn't ignorance, it's perfect understanding of a gap you cannot possibly close. Sometimes knowing exactly why you're losing is worse than the losing itself. This is the story of an engine that produced 2,000 horsepower, and the war that was already decided before the first bolt was removed. To understand what the Japanese engineers found in that hangar, you must first understand what they had built. You must understand the philosophy that created the Zero, and why that philosophy seemed so correct in 1940. The Mitsubishi A6M Zero wasn't merely an aircraft, it was an entire strategic vision made airborne. It was Japan's answer to a question that had plagued naval planners since carriers first put to sea. How do you project air power across the vast distances of the Pacific Ocean? Chief designer Jiro Horikoshi received the specifications for what would become the Zero in 1937. The Imperial Japanese Navy wanted something that seemed impossible. A carrier-based fighter with the range of a land-based bomber, maneuverability superior to any existing fighter, and the ability to escort attack aircraft deep into enemy territory. The design parameters were extraordinary, a range of at least 1,900 miles, a top speed exceeding 300 miles per hour, armament capable of destroying enemy fighters and bombers, and the ability to operate from the limited deck space of a carrier. The problem was physics. Range requires fuel. Fuel has weight. Heavy aircraft need powerful engines. Powerful engines add more weight. Weight reduces maneuverability. Every advantage comes at a cost, and the engineering challenge was to minimize those costs through radical efficiency. Horikoshi's solution was elegant, almost beautiful in its logic. If you couldn't make the engine more powerful without adding weight, you reduced the weight of everything else. Every component was scrutinized, lightened, refined. The airframe used an aluminum alloy developed specifically for weight reduction. The fuselage skin was thin enough that mechanics had to be careful not to dent it with their hands. The landing gear was designed to the absolute, minimum strength needed for carrier operations. Then came the truly radical decisions. No armor plating around the cockpit armor was heavy. No self-sealing fuel tanks, the rubber compounds added weight and reduced fuel capacity. No heavy defensive armament, every kilogram devoted to protection was a kilogram not devoted to range or maneuverability. The Japanese called this approach senshin selection and concentration. Focus resources on what matters most. In this case, What mattered was the ability to reach enemy forces before they could strike, engage with superior agility, and return home. The Zero would survive through speed and maneuverability, not armor. The pilot's skill would be the protection. And for nearly 2 years, this philosophy worked brilliantly. When Zeros first appeared over China in late 1940, they achieved complete aerial dominance. Chinese fighters couldn't touch them. The Zero could outturn anything in the sky, outclimb most opponents, and the range allowed Japanese carriers to strike from positions enemy commanders thought were impossible. In the opening months of the Pacific War, Zeros escorted bombers to Pearl Harbor from carriers nearly 250 miles away, a distance American planners had considered beyond the operational range of carrier aviation. At the Battle of the Coral Sea in May 1942, Zeros fought American Wildcats to a tactical draw. At Midway in June, Zero pilots shot down dozens of American aircraft. The kill ratios favored Japan. The Zero seemed invincible, its design philosophy vindicated by combat results, but the Americans were learning. More importantly, they were building. The Grumman F4F Wildcat was America's frontline carrier fighter in 1942, and it was outmatched by the Zero in almost every measurable way. Slower, less maneuverable, shorter range. But the Wildcat had something the Zero lacked. It could absorb tremendous damage and keep flying. Wildcats came, back to carriers with holes you could put your fist through. The self-sealing fuel tanks worked. The armor plating worked. Wildcat pilots developed tactics that avoided dogfighting. The thatch-weave formation allowed pairs of Wildcats to protect each other, turning the Zero's superior agility into a liability. And behind the Wildcat, Grumman was already building its replacement. The F6F Hellcat program began in June 1941, before Pearl Harbor, before America even entered the war. Grumman's designers had studied intelligence reports on the Zero and concluded that the future of fighter aviation wasn't elegant efficiency, it was overwhelming power married to survivability. The Hellcat would be bigger, heavier, more powerful, more heavily armed, and more heavily armored than any carrier fighter that had come before. When the first production Hellcats reached fleet squadrons in January 1943, Japanese pilots noticed the difference immediately. These American fighters weren't trying to turn with Zeros. They were diving from altitude, firing devastating bursts from 650 caliber machine guns, then climbing away before Zeros could respond. The Hellcat was faster in level flight. It could outclimb the Zero, it could outdive it, and when Zeros managed to get guns on target, the Hellcats absorbed the punishment and kept fighting. By mid-1943, the kill ratios had reversed catastrophically. Hellcats were destroying Zeros at rates approaching 20-1. 20 Japanese fighters lost for every Hellcat shot down. The numbers were so lopsided that American intelligence initially suspected Japanese reports were propaganda. But the pattern held across every engagement, every theater, every tactical scenario. The Japanese high command needed answers. What had the Americans done? What technology had they developed that could overcome the Zero's carefully balanced design? What was the secret? In late June 1943, they got their chance to find out. A Hellcat making an emergency landing on Japanese-held territory in the Marshall Islands suffered mechanical failure and ditched near the shore. The pilot survived and was captured, but the aircraft was recovered largely intact. The order came directly from Admiral Minachi Koga, Commander-in-Chief of the Combined Fleet. Transport that aircraft to Yokosuka. Take it apart. Find out how it works. The Hellcat was dismantled, packed into crates, loaded onto a submarine, transferred to a destroyer, and finally trucked to the Yokosuka Naval Air Technical Arsenal. The facility was Japan's primary center for aviation research and development, the best engineers, the best tools, the best technical library in the country. If anyone could unlock the Hellcat's secrets, it was the team at Yokosuka. They began with photography. Every angle, every panel, every component was documented before anything was touched. The Americans might bomb the facility happened regularly enough, and if the physical aircraft was destroyed, at least they'd have the photographs. Then came the measurements, overall dimensions first. The Hellcat was 33 feet 7 inches long, with a wingspan of 42 feet 10 inches when the wings were extended. Height at rest, 13 feet 1 inch. These were similar to the Zero's dimensions, a bit larger, but nothing extraordinary. Then they weighed it. A fully fueled and armed A6M Zero weighed 5,313 pounds. The Hellcat, in the same configuration, weighed 15,413 pounds, nearly 3 times heavier. Engineer Takahashi Masao, a specialist in aerodynamic design, wrote in his notes, "This cannot fly from a carrier deck. Wing loading is absurd. How does it generate sufficient lift at carrier takeoff speeds?" But it did fly, beautifully, according to combat reports, which meant the secret was somewhere in those additional 10,000 pounds. The weight wasn't arbitrary. The Americans had added that mass for specific reasons, and those reasons were winning the air war. They started removing panels. The outer skin of the Hellcat's fuselage and wings was substantially thicker than the Zero's. Where Japanese engineers used aluminum alloy sheets measured in fractions of millimeters, the Americans used heavier gauge material. The structural ribs and longerons were more robust, more closely spaced. The entire airframe was overbuilt by Japanese standards, engineered not just for strength, but for damage tolerance. Beneath the pilot's seat, they found a steel plate 3/4 of an inch thick. Behind the pilot's position, another plate of similar thickness. The windscreen was bullet-resistant glass, far heavier than the Zero's standard canopy. The armor added weight, yes, but the purpose was clear. American pilots were expected to survive being shot. The aircraft was designed to bring them home even after taking damage that would have destroyed a Zero. The fuel tanks revealed another design difference. The Hellcat's tanks were surrounded by a self-sealing rubber compound. When a bullet punctured the tank, the compound would expand and seal the hole, preventing fuel leakage and fire. The Japanese had experimented with similar technology in 1941, but abandoned it because the weight penalty reduced range and performance. The Americans had accepted that trade-off. They'd chosen survivability over efficiency. The armament bays revealed a different philosophy of combat. The Hellcat carried 6 Browning M2 50 caliber machine guns, 3 in each wing. Each gun was loaded with 400 rounds of ammunition. Total ammunition load, 2,400 rounds. By comparison, the Zero carried 2 Type 99 20mm cannons with 60 rounds each, and 2 Type 97 7.7mm machine guns with 680 rounds each. The Japanese loadout was designed for precision. A skilled pilot could destroy an enemy aircraft with a short burst from the cannons. Ammunition conservation was essential because weight was precious. The American loadout was designed for volume. 2,400 rounds meant a Hellcat pilot could hold the trigger down for more than 30 seconds of continuous fire across all 6 guns. They weren't expected to be precise. They were expected to saturate the target. Takahashi's notes from July 8th. The Americans are training their pilots to overwhelm targets with firepower. Our pilots are trained to make every shot count. 2 different philosophies. But their philosophy requires industrial capacity we do not possess. But none of this, not the armor, not the ammunition, not the structural overbuilding, explained the performance advantage. The Hellcat was carrying 10,000 pounds more weight than a Zero, yet it was still faster in level flight, still climbing better, still outperforming Japanese fighters in every measure except turn radius, which meant the answer was in the engine. On July 15th, 1943, the engineering team removed the Hellcat's engine cowling. The process took 4 hours. The cowling panels were secured with over 60 fasteners, and the team was meticulous about documentation. Every fastener was catalogued. Every wire was photographed before disconnection. When the cowling finally came away, revealing the engine in its mount, the hangar fell silent. The Pratt and Whitney R2-800 double Wasp radial engine sat before them like something from a different era of technological development. 18 cylinders, arranged in 2 rows of 9. Displacement, 2,804 cubic inches. Dry weight, 2,360 pounds heavier than many complete aircraft engines Japan was producing. And the power output, 2,000 horsepower at war emergency power settings. 2,000 horsepower. The Zero's Nakajima Sakai engine produced 1,130 horsepower at takeoff power. Even Japan's most advanced fighter engines, still in development, were targeting 1,500 horsepower as an ambitious goal. The Americans had built an engine that produced nearly twice the power of Japan's frontline fighter engine. And they'd made it reliable enough for carrier operations, compact enough to fit in a single-engine fighter, and most remarkably, they were manufacturing it in quantity. Lieutenant Commander Genda stood in front of the exposed engine for a long time. Other engineers moved around him, taking measurements, setting up photography equipment, preparing for the detailed analysis. But Genda just stood there, looking at the 18-cylinder monster, doing the calculations in his head, power-to-weight ratios, fuel consumption rates, manufacturing tolerances, industrial capacity requirements. According to later accounts, he said nothing during those minutes of silence, but when he finally turned away from the engine, one of the junior engineers asked him what he was thinking. Genda's reply, recorded in the facility's log, "I'm thinking about how we will lose this war." The engineering team spent the next 3 weeks systematically measuring, documenting, and analyzing every component of the R2-800 engine. They weren't trying to understand how it worked. Radial engine theory was well established. They were trying to understand how it was made. The cylinder heads were removed and examined under microscopes. The metallurgy was sophisticated alloys that could withstand extraordinary heat and pressure without deforming. The machining tolerances were incredibly tight, far beyond what Japanese manufacturers routinely achieved. The Americans were using advanced machine tools and quality control processes that Japan's industrial base couldn't replicate at scale. The supercharger system was particularly revealing. A 2-stage supercharger allowed the engine to maintain power output at high altitudes, where naturally aspirated engines would lose performance. The engineering was elegant, but the manufacturing requirements were prohibitive. Precision gearing, tight tolerances, specialized bearings. The fuel injection system was designed for high-octane aviation fuel. The Japanese had intelligence suggesting the Americans were using 100-octane or higher fuel for their frontline fighters. Japan's best aviation fuel was 92-octane. Higher-octane fuel allowed higher compression ratios, which produced more power. But producing high-octane fuel required sophisticated refining capacity and access to specific chemical additives. Japan's petroleum industry couldn't match American fuel quality, even if the raw materials were available, which they increasingly weren't. Every system they examined pointed to the same conclusion. The R2-800 wasn't just a more powerful engine. It was a product of an entirely different industrial and resource ecosystem. On August 9, 1943. The Yokosuka team submitted their comprehensive report to the Imperial Japanese Navy General Staff. The document ran to 147 pages, including technical drawings, metallurgical analyses, and manufacturing assessments. The executive summary was devastating in its clarity. The R2-800 engine achieves its performance through the integration of advanced metallurgical processes, precision manufacturing capabilities, and high-octane aviation fuel. Each of these elements presents significant challenges for domestic reproduction. The metallurgy requires alloys incorporating chromium, molybdenum, and nickel in quantities that exceed our current strategic reserves. The manufacturing precision demands machine tools and quality control systems that exist in only limited numbers within the Japanese industrial base. The fuel requirements cannot be met by our current refining capacity. Furthermore, intelligence estimates suggest the Americans are producing these engines at a rate exceeding 2,000 units per month from multiple manufacturing facilities. Our entire aircraft engine production across all manufacturers and all types currently averages approximately 1,500 engines per month. The Americans have dedicated more production capacity to a single engine type than we possess for our entire aviation program. The technological gap is not primarily one of design philosophy or engineering knowledge. We understand how this engine functions. The gap is one of industrial capacity, resource availability, and manufacturing infrastructure. The Americans have not built a superior fighter by being more clever. They have built a superior fighter by having access to effectively unlimited industrial resources and raw materials. The report included a section that was remarkable for its bluntness unusual in Japanese military documents of the period where bad news was often softened or obscured. The section was titled, Assessment of Replication Feasibility. Can we build an equivalent engine? Yes. Given sufficient time and resources. Can we build it in quantities sufficient to affect the strategic situation? No. The industrial capacity required to manufacture engines of this type at scale would require reorganizing our entire aviation production system, retraining our workforce, acquiring machine tools that must be either manufactured domestically or imported, and securing access to raw materials that are currently difficult or impossible to obtain due to enemy interdiction of shipping routes. Timeline for limited production capability, 18 to 24 months. Assuming optimal conditions and no disruption from enemy action. Timeline for production at strategically relevant scale, not achievable within the probable duration of the current conflict. The report was distributed to senior naval commanders, Army Aviation Staff, and the Cabinet Planning Board. Everyone now knew exactly why the Renjo air war was being lost. The knowledge was perfect, detailed, and utterly useless. Admiral Koga read the report and requested a meeting with the Yokosuka engineering team. The meeting took place on August 20th, 1943, in a conference room overlooking Tokyo Bay. 15 officers attended, including representatives from Mitsubishi, Nakajima, and Kawanishi, Japan's primary aircraft manufacturers. The question posed to the engineers was simple. Given what you've learned, what do you recommend? The lead engineer's response, recorded in meeting minutes, we recommend immediate development of interim improvements to existing fighters while pursuing long-term engine development programs. We cannot build the R2-800. We can potentially build something better than what we currently have, but we must recognize that the Americans are not standing still. While we develop improvements, they are producing in quantity. The strategic implication is that pilot skill and tactical innovation must compensate for material disadvantage. One of the Mitsubishi representatives asked the obvious question, for how long can skill compensate for material disadvantage? Silence. Then Genda spoke, until the skilled pilots are dead, then we lose. The bluntness shocked the room. Japanese military culture valued fighting spirit Yamato Damashi as a counter to material disadvantage. The idea that courage and skill had limitations was not typically voiced in official settings. But Genda continued, the Americans are training pilots in enormous numbers. Their training programs are 6 months long. They're not producing exceptional pilots. They're producing competent pilots who know their aircraft's advantages. Our pilots train for years and are individually superior. But when an exceptional pilot in an inferior aircraft fights a competent pilot in a superior aircraft, the outcome is not certain. When that exceptional pilot faces 3 competent pilots in a superior aircraft, the outcome is almost certain. And when that exceptional pilot is killed, we cannot replace him quickly. We're trading quality we cannot quickly replenish for the quantity they produce continuously. The meeting ended without a formal decision. There was no decision to make. Japan would continue developing improved fighters. The A7M Repu was already in development, designed to match or exceed the Hellcat's performance. The Kawanishi N1K Shiden was being refined. Engine manufacturers would pursue higher power outputs. But everyone in that room understood the fundamental problem. They were trying to catch up to a moving target, and the target was accelerating while their own capacity was constrained by resources they didn't have and couldn't obtain. The war continued. The Hellcat continued its dominance. In November 1943, Hellcats participated in the assault on Tarawa. They provided air cover for the landing forces and swept Japanese aircraft from the skies with minimal losses. In February 1944, during Operation Hailstone, the American raid on Truck Lagoon Hellcats destroyed approximately 270 Japanese aircraft over 2 days of combat. The Japanese lost irreplaceable pilots, aircraft, and the strategic naval base they'd considered impregnable. Japanese manufacturers tried to respond. Mitsubishi pushed the A7M Repu program, which aimed to create a fighter matching the Hellcat's speed and firepower while retaining superior maneuverability. The first prototype flew in May 1944. Test pilots were impressed it was fast, heavily armed, and agile. It could match a Hellcat in most performance categories and potentially outfight it in skilled hands. But the Repu faced the same resource constraints the Yokosuka engineers had identified. The engine required materials that were increasingly scarce. The manufacturing precision needed for the sophisticated systems exceeded the capabilities of many Japanese factories, which were now operating with inexperienced workers as skilled laborers were conscripted for military service. American bombing raids disrupted production. Earthquakes damaged facilities. Japan's factories weren't just fighting industrial competition, they were fighting geography. By the time production repus were ready for combat operations, only 9 had been built. 9 aircraft. The Americans were producing over 3,000 Hellcats per month by mid-1944. Kawanishi had better success with the N1KJ Shiden Kai, the George, in American code names. The Shiden Kai was arguably the finest fighter Japan produced during the war. It could match or exceed the Hellcat in most performance categories. Japanese pilots who flew it praised its handling, firepower, and speed. In competent hands, a Shiden Kai was a dangerous opponent for any American fighter. Approximately 1,400 were built before the war ended. By comparison, 12,275 Hellcats were produced. The numbers told the story. Japan could design competitive aircraft. Japanese engineers understood the principles. Japanese pilots were skilled and determined, but the industrial capacity gap was insurmountable. For every advanced Japanese fighter that reached a combat unit, the Americans were producing nearly 10 Hellcats. The human cost of this disparity played out in the skies over the Pacific with brutal consistency. In June 1944, the Battle of the Philippine Sea became what American pilots would call the Great Marianas Turkey Shoot. The Japanese committed approximately 473 carrier-based aircraft to stop the American invasion of Saipan. They faced American carrier groups equipped primarily with Hellcats. The result was catastrophic. The Japanese lost 336 aircraft over 2 days of combat. American losses, 30 aircraft. The kill ratio approached 20-1, exactly what the Yokosuka engineers had feared when they calculated the implications of the power-to-weight advantage. Japanese pilot accounts from survivors describe the hopelessness of the engagement. They would dive on American ships, only to be intercepted by Hellcats that climbed faster, hit harder, and could absorb damage that would have destroyed a Zero. The few Japanese pilots who managed to break through the fighter screen found themselves facing massed anti-aircraft fire from American ships equipped with proximity-fused shells and radar-directed guns, more technological advantages the Japanese couldn't match. After the Philippine Sea battle, Japanese naval aviation never recovered. The carrier force still existed, ships, hangars, fuel systems, but the trained pilots were gone. The replacements were rushed through abbreviated training programs that couldn't replicate the years of peacetime preparation that had created the elite pilots of 1941 and 1942. By late 1944, Japanese pilots had an average of 100 hours of flight training before combat deployment. American pilots averaged over 300 hours. The skill gap had reversed. And now the Japanese pilots, less experienced than their American counterparts, were flying inferior aircraft in smaller numbers against an enemy with total tactical initiative. The desperation showed in the tactics. In October 1944, the Japanese began organized kamikaze operations, deliberately crashing aircraft into American ships. The tactic was born partly from tactical calculation. A damaged aircraft could still damage a ship if deliberately aimed, but also from the recognition that conventional aerial combat was no longer viable. Japanese pilots in outdated aircraft couldn't survive long enough in combat to matter, but they could, potentially, cause damage through suicide attacks. The kamikaze campaign revealed the depth of Japan's material crisis. They were expending pilots and aircraft resources that couldn't be replaced to achieve tactical results that couldn't change the strategic situation. The attacks caused casualties and damage, but they couldn't stop the American advance. American industrial capacity could replace losses faster than kamikazes could inflict them. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The Hellcat continued flying combat operations through the war's end. It participated in the Philippines campaign, the battles for Iwo Jima and Okinawa, and the final air raids over Japan proper. Hellcats shot down Japanese aircraft over their own homeland, the ultimate demonstration of the air superiority gap that had opened since 1943. By August 1945, the tactical situation had evolved beyond anything imagined in 1943. American carriers operated within sight of the Japanese coast with near impunity. The Japanese air forces, both Navy and Army, had been reduced to a fraction of their peak strength. The pilots were inexperienced, the aircraft were often obsolete, and fuel shortages meant even available aircraft often couldn't sortie. The knowledge gained from studying that captured Hellcat in July 1943 had changed nothing. Every prediction the Yokosuka engineers made had come true. The industrial capacity gap proved insurmountable. The resource limitations proved fatal. The Americans had won the production war before the first bomb fell on Pearl Harbor, and the combat outcomes flowed inevitably from that industrial advantage. After Japan's surrender, American technical intelligence teams arrived at what remained of the Yokosuka Naval Air Technical Arsenal. Much of the facility had been destroyed in bombing raids through 1944 and 45, but some documentation survived, including portions of the Hellcat analysis report. The United States Strategic Bombing Survey, a comprehensive study of the air war's effects, conducted extensive interviews with Japanese engineers, military officers, and industrial managers. The goal was to understand what had worked, what had failed, and what lessons could be drawn from the conflict. Several of the Yokosuka engineers who had studied the captured Hellcat were interviewed in late 1945 and early 1946. Their reflections provide insight into how the experience felt from the Japanese perspective. Takahashi Masao, the aerodynamics specialist who had written those initial notes about the Hellcat's absurd wing loading, was asked by American interviewers whether studying captured enemy equipment had provided useful intelligence. His response, translated from Japanese, "We learned everything and nothing. Everything about the machine, we understood it completely. Nothing about how to match it." The Hellcat was not mysterious. It was obvious. Obvious in its purpose, its design, its manufacturing. The mystery was not how it worked. The mystery was how to build a nation that could produce such machines in such numbers. He continued, "To Japanese eyes, the Hellcat was wasteful, heavy, crude in some respects. We built aircraft by subtracting weight until only essential elements remained. The Americans built by adding capability until the airframe could barely contain it. Neither approach is wrong, but their approach requires resources we did not possess. You asked if studying the Hellcat was valuable. It was valuable in the way that understanding your own weakness is valuable. It clarified our situation. It did not improve it. Another engineer, whose name was not recorded in the interview transcripts, was more direct. We took apart the engine and understood every component. We calculated the manufacturing tolerances, the material requirements, and the quality control necessary. Then we looked at our factories and realized we were attempting to compete with a nation that could waste aluminum, waste steel, waste fuel. To us, every gram was precious. To the Americans, abundance was the strategy. The Hellcat wasn't elegant. It was American. Powerful because it could afford to be. The interviews revealed a consistent theme. Japanese engineers and military planners understood the technical details, but were stunned by the strategic implications. They had been fighting a war of efficiency against an enemy practicing a war of abundance, quality against quantity, refinement against overwhelming industrial capacity. One naval officer, asked about the Hellcat's impact on Japanese tactical thinking, stated, "After we understood what we faced, we had three choices. First, attempt to match American production impossible given our resource constraints. Second, develop tactical innovations that negate their advantages possible in individual engagements but not sustainable across the theatre. Third, accept that the material balance was against us and seek political resolution. We pursued the second option because the third was culturally and politically impossible until it was too late." The Americans found partial remains of the captured Hellcat during their survey of Yokosuka. The aircraft had been destroyed in a bombing raid in February 1945, along with most of the technical documentation the engineers had so carefully compiled. Ironically, the destruction came from a raid launched from carriers whose fighter cover included Hellcats, the descendants of the very machine that had been studied so meticulously. The final accounting of the Hellcat's combat record provides numerical validation of everything the Japanese engineers feared. The F6F Hellcat achieved a confirmed kill ratio of 19:1, enemy aircraft destroyed for every Hellcat lost in combat. This ratio held across the entire Pacific theater, across all combat conditions, and across the full duration of the Hellcat's service. It wasn't a statistical anomaly or the result of a few exceptional engagements. It was the consistent outcome of systematic material and tactical advantage. The Hellcat was credited with 5,223 confirmed aerial victories, more than any other Allied naval fighter. It participated in every major Pacific naval engagement from Tarawa through the final raids on Japan. Hellcat pilots included Medal of Honor recipients, multiple aces who scored 10 or more victories, and ordinary pilots who flew combat missions, survived, and went home because their aircraft could protect them. Production numbers tell their own story. Grumman manufactured 12,275 Hellcats between June 1942 and November 1945. At peak production in 1944, the company was delivering over 500 Hellcats per month from its Bethpage, New York facility alone. The United States Navy and Marine Corps received these aircraft, along with Britain's Fleet Air Arm, which operated Hellcats in the Pacific and Indian Ocean theaters. By comparison, Japan produced approximately 10,400 Zero fighters of all variants throughout the entire war, starting from production that began in 1940. The A6M Repu, designed specifically to counter the Hellcat, 9 completed aircraft. The N1K Shidenkai, arguably Japan's best fighter, approximately 1,400. The Pratt and Whitney R2-800 engine that had so impressed the Yokosuka engineers remained in production long after the war ended. It powered not just the Hellcat but also the F4U Corsair, another dominant American fighter, and various other military and civilian aircraft. Total production exceeded 125,000 engines. It was selected for reliability, ease of maintenance, and that overwhelming power output that Japanese engineers measured with precision and could not replicate. The engine represented more than just horsepower. It represented an industrial system that could design complex machinery, manufacture it with precision, produce it in enormous quantities, distribute it across a global logistics network, maintain it in harsh field conditions, and continuously improve it based on combat feedback. Every aspect of that system was beyond Japan's capacity to match. The story of the captured Hellcat contains layers of irony that extend beyond the immediate technical disparity. Japanese intelligence had correctly identified American industrial capacity as a strategic threat long before Pearl Harbor. The Japanese Navy's own planning documents from 1940 acknowledged that prolonged conflict with the United States would favor American production. The attack on Pearl Harbor was partly motivated by the belief that a decisive early blow would force political settlement before American industry could fully mobilize. That calculation proved catastrophically wrong, but not because Japanese planners misunderstood American capacity. They understood it correctly. They simply hoped to avoid having to face its full implications. The captured Hellcat represented the fulfillment of their fears, the moment when hope confronted reality, and reality won decisively. The Japanese engineers who studied the Hellcat were among the most skilled in their nation. They understood aerodynamics, metallurgy, propulsion, and manufacturing. Their technical competence was not in question. But competence cannot overcome resource constraints. Knowledge cannot substitute for industrial infrastructure. Understanding does not create strategic options where none exist. This is perhaps the cruelest lesson of the Hellcat analysis. Intelligence can make a bad situation clearer without making it better. The engineers gave their commanders perfect information about why they were losing. That information changed no material facts. American production continued. Japanese resources continued dwindling. The war continued to its inevitable conclusion. There's a broader historical question embedded in this story. Could Japan have won the Pacific War through industrial competition? The answer, based on every objective measure, is no. American gross domestic product in 1941 was approximately 10 times larger than Japan's. American steel production was 12 times larger. American oil production was hundreds of times larger. The United States had geographical advantages, oceans protecting the homeland from direct attack, allowing industrial infrastructure to operate without disruption. It had resource advantages, domestic supplies of oil, coal, iron, aluminum, and agricultural products sufficient to feed both the civilian population and military forces. Japan had to import most strategic resources through sea lanes that became increasingly vulnerable to American submarine and air attack. By 1944, Japanese oil imports had dropped to a fraction of 1941 levels. Without oil, the impressive fighters Japan designed couldn't fly. Without steel, they couldn't be built. Without food imports, the workforce couldn't be sustained. The Hellcat's 2,000 horsepower engine was impressive, but the real power gap was measured in mines, refineries, factories, and farms. The Americans could afford to build heavy fighters because they could afford the fuel to fly them, the carriers to launch them, and the logistics network to support them. Japan could design equivalent aircraft but couldn't build them in relevant numbers because the entire supporting infrastructure was lacking. The engineers at Yokosuka understood this. Their report made it explicit. But understanding doesn't equal ability. They could explain why Japan was losing. They couldn't change the facts that ensured Japan would lose. In the final months of the war, as American forces approached the home islands, Japanese aircraft production actually increased in some categories. Desperate measures dispersed manufacturing, underground factories, simplified designs allowed continued output even under heavy bombing. But the aircraft produced in those final months were increasingly obsolete, flown by insufficiently trained pilots, and fueled by aviation gasoline so poor it damaged engines. The Yokosuka facility where the Hellcat had been studied was repeatedly bombed through 1944 and into 45. Engineers dispersed to satellite facilities. Some documentation was lost. Some were deliberately destroyed as American forces neared. The institutional knowledge remained. Engineers remembered what they'd learned, but the opportunity to apply that knowledge had passed. Japan's last significant aerial resistance came during the Okinawa campaign in spring of 1945. Conventional air combat had become suicidal for Japanese pilots facing American fighters with total performance superiority. Kamikaze tactics predominated not because they were effective, but because they were the only tactic that allowed obsolete aircraft flown by inexperienced pilots to potentially inflict damage. Hellcats intercepted kamikaze raids, shooting down hundreds of attackers before they could reach the American fleet. Some kamikazes got through individual determination can sometimes overcome material disadvantage in single engagements, but strategically, the kamikaze campaign demonstrated the complete collapse of conventional aerial capability. Japan was expending pilots and aircraft as ammunition because conventional tactics no longer worked. The final American air raids over Japan in July and August 1945 met minimal resistance. Japanese fighters rose to intercept, but in small numbers, often with insufficient fuel for sustained combat. American fighters, Hellcats from carriers, along with land-based P-51 Mustangs operated over Japanese cities with near impunity. The atomic bombings of Hiroshima and Nagasaki in August received no aerial opposition. Japan no longer had the capacity to contest American air superiority over its own cities. When Emperor Hirohito announced surrender on August 15, 1945, the decision was influenced by many factors: the atomic bombs, Soviet entry into the war, the complete naval blockade, the destruction of cities by conventional bombing. But underlying all these immediate causes was the fundamental imbalance that the Yokosuka engineers had identified 2 years earlier. Japan could not compete industrially with the United States. Every strategic calculation led to the same conclusion: the war ended. The engineers survived most of them. Their knowledge of American aviation technology was suddenly valuable again, but in a different context. Post-war Japan would rebuild, eventually becoming an industrial power. But in 1945, the engineers of Yokosuka faced the personal cost of perfect knowledge. They had understood exactly why their nation lost, had documented it precisely, and had been unable to prevent it. Takahashi Masao, the engineer who had studied the Hellcat so carefully, was interviewed again in 1952. Japan was occupied, rebuilding, transforming. The interviewer asked if he had any final thoughts about the Hellcat analysis. His response: "I spent 3 weeks measuring that engine. I can still recall the specifications precisely. 2,000 horsepower, 18 cylinders, 2,804 cubic inches displacement. I understood it completely, and that understanding taught me humility. We were not defeated by superior knowledge. We were defeated by superior resources, applied with competent knowledge." The Americans did not need to be brilliant. They needed to be thorough and have access to unlimited industrial capacity. They had both. He paused, then continued, "When I see American aircraft now, flying over Japan with occupation forces, I do not think of them as enemies. I think of them as evidence. Evidence that wars are not won by elegant engineering alone. They are won by nations that can waste material and still have abundance." The Hellcat could afford to be heavy because America could afford the fuel to fly it, the carriers to launch it, and the industrial base to build thousands of them. We could not afford any of those things. That was the gap. Not horsepower. Everything else. The captured Hellcat at Yokosuka revealed a truth that Japanese military planners had suspected but hoped to avoid. Material wars are won by material advantage. Skill matters. Determination matters. But when the resource gap is large enough, skill and determination become tragic rather than decisive qualities. The engineers who studied that aircraft gave their commanders exactly what was requested: perfect intelligence about enemy capabilities. The intelligence confirmed the worst-case strategic assessment. It provided no solutions because no solutions existed within Japan's resource constraints. This is the final irony. The most valuable intelligence is sometimes the intelligence that tells you the situation is hopeless. Not because hopelessness is desirable, but because false hope is dangerous. The Yokosuka engineers gave Japan's leadership a clear-eyed assessment of reality. Whether that leadership could have acted differently based on that assessment is a question historians continue to debate. What is not debatable is the technical accuracy of their analysis. They correctly identified the performance gap. They correctly assessed that the gap could not be closed given available resources. They correctly predicted that pilot skill would prove insufficient to compensate for material disadvantage. They were right about everything, and it changed nothing. The Hellcat flew on. The war ended. The engineers returned to civilian life. The knowledge they gained from studying that captured aircraft became a footnote in technical histories, interesting to specialists, forgotten by most. But for those who understand what that analysis represented, the moment when perfect intelligence revealed an insurmountable gap, the story carries weight beyond its immediate historical context. Sometimes knowing exactly why you're losing is the most painful knowledge of all, because it strips away illusion without providing hope. It clarifies reality without changing it. The Japanese engineers at Yokosuka didn't discover a secret weapon they could copy. They discovered a mirror, and in it they saw a war that was already lost, measured in horsepower, production rates, and industrial capacity they could never match. 2,000 horsepower, that was the gap. Not just in engines, in everything. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.